All right, so today we're going to be talking about entropy, second and third laws of thermodynamics, which define entropy. Although you guys are already experts in entropy because of the stat thermo that we did. So you guys really have, I would say, a deeper or better understanding about entropy than scientists had for the first 100 years of using the term entropy. Um, and then also much better than your peers who didn't do the stat thermo piece like at other schools. So you understand that entropy is driven by the number of options in the room or in the energy level diagram. So something with a degeneracy of 2 is going to be favored than if they're the same energy than something with a degeneracy of 1, because there's 2 chairs over here. And if we roll the dice and we put a split in between reactants and products, the products are going to dominate because there's 2 chairs over there and only 1 chair over here. So that's entropy. That's entropy driving that forward, is because you have more options. So just in general, gases have much higher entropy than liquids and solids. So if something produces a gas as a product, entropy is greatly increasing. Okay, so those are some things that you should have as intuition in the background. Because when you get into the math, it's hard to track it. It's just a bunch of variables and numbers and so on. But conceptually, things that are higher temperature have more entropy. Things that have more options, like the translational energy levels, are so close together that they're touching almost. And so remember, our partition function for translational motion was orders of magnitude, like 10 to the 9, 10 to the 30, huge. So if it produces a gas, it produces a lot of populated energy levels. There's a huge partition function. And so let's look at this heat capacity. Is, again, we're storing energy in molecules, in gases, liquids, solids. And so it's the amount of energy that goes in that would raise that substance a degree in Kelvin. So it's the heat capacity. Boltzmann's constant in general is that conversion from joules to Kelvin or Kelvin to joules. If I raise the temperature of a gas a certain amount, Boltzmann's constant in its various forms, like the gas constant R and so on, would tell me how many joules I stored in that substance at a given temperature. So we can get that. So this is the heat capacity, the capacity of it to store heat. And so we've done a lot of this with the CV, the heat capacity constant volume. And so here we have it for water, polyatomic gases, and so on. So notice that the liquid water is quite a bit higher than polyatomic gases. It's 3 times higher. The way I kind of see this is for the gas, for water, we have the translational motions. That's 3 halves R. And then we have the rotational motions. Since it's nonlinear, there's 3 of those. We have 3 halves R of those. So we get 3 R values for the translation and rotational motion. And that's 25 roughly. It's, 3 times 8 is 24 and some change. Okay. So this polyatomic gas for water, the translation and rotational motion accounts for all 25 joules per mole per Kelvin. But then we go to liquid water, and we're not still activating the vibrational stretches of the hydrogens because they're so lightweight that we don't have enough temperature and room temperature and so on to activate those. But when you make liquid water, you have whole molecules bouncing against each other. And so if you take a whole molecule in water now, instead of translating, it's bumping into its nearest neighbors. And you got to have 2 neighbors for it to bump into, right? The water bumps into this one along the x-axis. Well, that neighbor's on the x-axis. So it's sort of like a whole molecule vibration in the x direction. So we got 2 molecules sort of vibrating against each other. Vibrational motion gives you a unit of R to your heat capacity. Well, I could have a molecule in the y direction too, and that vibration would give me a unit of R. And then along the z-axis, that molecule, that vibration inside the liquid would give me a unit of R. So we got 3 more units of R, so we've got another 25. And so now we're up to 50. And so then you've got nearest neighbors, maybe diagonals and so on, giving you 3 more. And so that's how we can understand in a liquid or in a solid the heat capacity, because it's whole molecules moving around and banging into each other. So we can store energy in those. Now, this isn't a translation. It's like a sound wave. So if I bang one end of a container of water, the shock wave goes through the water. What's carrying that shock wave? It's water molecules banging into each other. And that's the same process as sound. And so those are not called vibrations or rotations or translations. They're called acoustic modes because they're whole molecules banging into each other, which is what you get with sound traveling through a substance. And so that's an acoustic motion. And so this higher heat capacity for water and other solids and liquids are resulting from the acoustic modes. And they're vibration-like. You also have rotations, but it can't freely rotate. So water, if it tries to freely rotate in a liquid or a solid, it turns and bangs into its nearest neighbors. So it's like a partial rotation. So the hydrogen is too close to something, and so it's turning and it's banging into it like that. So as water's trying to rotate, it can't. And so they've made up a term for that too. It's not an acoustic mode. It's not shifting the whole way in the liquid. It's sort of hindered rotation. And that's called a libration. L-I-B, like instead of vibration, it's a libration. So those are the strange things that we're thinking of in terms of our liquids and solids that give it a much higher heat capacity, 75 versus 25, 3 times more. So you have 3 librations, you have 3 acoustic modes, and so you get 6 more R to store heat in. So we can store more heat into a liquid than we can into a gas. For every degree Kelvin. Now, heat capacity is per mole, and sometimes you see the word specific put in there. Whenever we're talking about specific heats, it's per gram. So you want to take a note of that too, because in your lab, the QSPR lab today, we're going to talk about specific heat, and we're going to talk about heat of combustion, and specific heat of combustion would be per gram or per kilogram of substance, per mass. And then we have the internal energy. So if we know the CV, we can multiply by the delta T, and we can get the internal energy of a substance. And so since work is 0 at constant volume, the change in temperature with heat input can be used to determine CV. And so that's one of the things that we'll do in our calorimetry labs. So let's review the equations so far, because that's the downside of thermodynamics is we have so many equations, it's bewildering. So you're going to have a really small print note card. Okay, so you can put all these equations on there. You saw it with the USAG equations and so on. So far we've had internal energy, we've had irreversible expansion, so expansion against a constant pressure. So this was the piston example. We're pushing against a piston that has a constant external force. This is also the equation we use for, say, open beakers. So it produces a certain amount of gas, like the iron reacting with acid to produce hydrogen gas. That hydrogen gas escaped and pushed back against a constant pressure of 1 atmosphere, made 24.6 liters, and it did this amount of work. Okay, we used this conversion factor to get out of liter atmospheres and into joules. So this was a useful thing too. So that's definitely a note card item there. And then we had the isothermal reversible expansion. And so this was the natural log. We did that integral and got the natural log of the volumes. And so at constant volume, this is our heat capacity, and it's able to turn the change in temperature into internal energy. So this is all on the internal energy side. We're going to really get into enthalpy too. Enthalpy is at constant pressure. So at constant pressure, we have this equation where the change in enthalpy is the heat of reaction at constant pressure. And notice now we have a new heat capacity. So this is new. We haven't really seen this until now. This guy right here. Good morning. That just doesn't make any sense. Let me improve my handwriting, please. Okay. So it's the same concept. It's the same. It's heat capacity. How much energy goes into a substance for every degree Kelvin, but it's at constant pressure. And so this is a way to determine the enthalpy of reaction if we know the heat capacity and we know the temperature change, or if we know the change in heat and the temperature that went with it, we could solve for the heat capacity at constant pressure. And so here are the thermodynamic definitions of these heat capacities. It's the derivative of energy with respect to temperature at constant volume, that's CV, and then the derivative of enthalpy with respect to temperature at constant pressure is the CP. And then this is, I put a red box on it, it's super important. So if we know one, we can get the other. So we can go from heat capacity constant volume, which you guys learned how to do for gases, right? You can do the translational motion, the rotational motion. We can ignore the vibrations at room temperature for small molecules. We have CV. Just add one more unit of R, and now we have CP. So you can do this for gases very easily. So I'll do that. Easy. And we will do that. So we're going to do heat engines where we have a working gas, whether it be like a helium, where it's a monatomic gas and you only have translation, or maybe it's nitrogen and oxygen where you have linear molecules, so you have 5 halves R, or it's for a nonlinear molecule like water or something like that. Okay, now let's get into the second law of thermodynamics. All of that was review, with the exception of the CP stuff. And so this is a statement of the second law. No cyclic process is possible in which the sole result is the absorption of heat from a reservoir and its complete conversion into work. Now, we did have this example of isothermal reversible expansion work. So we're on an isotherm. This right here is the PV curve with constant temperature. So that's the isothermal piece. We have a fixed number of moles, and we have a gas constant. So all of those are constant. And so it's like plotting 1 over V, right? It's P is a constant divided by volume. And so it is this what do you call those curves? Where they're asymptotic at the top and the bottom. Just the 1 over X, essentially. And so that's, what's that? No, it's not a logarithm. But anyway, it's just pressure is a constant over volume. It's inversely proportional. Okay. And so you have these are called isotherms. It's an isothermal expansion, so it follows that isotherm, and we can calculate the work that's done during that. And so here's the work that's done. If we know the final and initial volumes, we know the temperature, it's a fixed value, we know the number of moles and the gas constant, we can calculate the amount of work. Okay. This has also caused a change in internal energy, but because delta T is 0, this is 0, it's an isotherm, then the internal energy is equal to 0. So we have a 0 change in internal energy. And the first law of thermodynamics tells us we could change that energy with heat, or we could change that with work. But this is telling us there's no change in energy, but that doesn't mean that heat and work are 0. We're obviously doing work. And how are we able to do work? Well, we're able to do work because we're sucking heat out of the hot reservoir and converting it into work directly. So the work is equal to minus Q. So this seems to be a violation of the second law of thermodynamics. Look what we're doing. We're absorbing heat, right? The sole result of this process is we're absorbing heat from a reservoir and completely converting it into work. So this seems like a violation of the second law of thermodynamics, but it's not, because the second law says no cyclic process is possible. So this is not a cyclic process. This is one leg of a cycle. So what is a cycle? Well, a cycle would be we expand out to volume final using an isotherm, and then we expand again a little further using an adiabat. An adiabatic curve. And I'm going to put in parentheses temp drops. So in an adiabatic expansion, the temperature changes. So we go from that hot reservoir down, the temperature starts to drop. We're expanding so much that we can't get any more heat out of the hot reservoir because it's either going too fast or what. There must some mechanism where this isotherm, as you're coming down, changes to an adiabat and it drops steeper, and you end up changing temperature. The gas cools down, which that's typical. What your typical experience is. If you were back in the day, I don't know if there's, I mean, maybe they still sell it, but back when I was a kid, the only deodorant you could buy was spray. Like Right Guard was the popular brand at the time, and so you would spray this under your arms to put on your deodorant, and it was freezing cold. And as a kid, as a little scientist, right, I'm like, that's weird because the can's not cold, and the gas is in the can, so I don't think the gas is cold. So why is it cold when you spray it on? Does that make sense? I mean, why? What's cooling it down? Expansion. So the gas is under pressure. It comes out the nozzle. It expands. And what happens when it expands? At a molecular level, all the little intermolecular attractions are breaking. Right? So you have this intermolecular attraction. You break it. Where'd the energy come from to break that attraction? Nowhere. Right? And so the gas cools down. It has to use up the energy it has inside to break that attraction. So it sucks the energy out of itself by expanding, and it cools down. And that's what's happening at an adiabat. So when an adiabat expansion, you get a drop in temperature, and now you have two legs of a cycle. So we've got one here. This is the second leg. Now, what if we want to reuse this gas? We could compress it. So if we compress it along an isotherm, it'll be somewhat parallel to that other one, but it's going to be cold. And so this one up here was hot, right? It's higher pressure at a given volume, so it's certainly hotter. Does that make sense? A higher pressure at a given volume, it's hotter. And then the adiabat, it cooled down, so we're at a colder temperature. We compress it along that cold reservoir. So as we're compressing it, the gas wants to heat up, but we're sucking the heat of compression out because it's in a cold bath. And we'll learn more about these cycles as we go along. And then eventually it can't suck any more heat into that cold bath, and so then we have an adiabat back up, and that's when the gas heats up. So we're compressing that gas, and we're heating it up. And if you're ever if you have a compressor, I don't know how many college kids have compressors in their dorm rooms and so on, probably very few. But in the future, when you have your own vehicles and you want to check your tires, you probably buy a compressor. And you turn it on and it compresses air into a tank. And you'll see between the compressor and that tank some heat fins. Because when it compresses that gas, the gas heats up. Okay? Just like expanding a gas cools it down, compressing a gas heats it up. Why is that? Well, the gas is getting closer and it starts to interact with other gas molecules. That releases energy. So it's kind of like they're bonding, but they're not molecularly bonded. They're just van der Waals forces. They get close enough to stick. Well, when they stick, they release energy. And so that heat has to be taken out of the system. And so that's why and don't be stupid like me. You got the compressor running and you touch that hot side where all the heating coils are to see how hot it is. This is the heat of compression, and it's pretty darn hot. I didn't blister my finger, but it was hot. Yeah. Okay. So this is a cycle. Notice we're back to where we began. And in terms of energy, remember the second floor? It didn't matter if I got there by coming down the stairs or going up the stairs. So that point on our cycle, the energy is back to where it was. If I had the same pressure, temperature, and number of moles and volume, my four state variables, I have the same energy. I've gone all the way around and I'm back to where I was. I'm back to the same energy. The energy I released when I did the expansion has been put back into the system by compression. And this is a cycle. And this is what Lord Kelvin is saying is impossible. to do this whole cycle where heat was absorbed from the hot reservoir and completely converted into work. Um, we'll see why that is, and it's because of entropy, and also because this cold side would have to be 0 Kelvin for it to completely turn that heat into work, and we can't have a cycle in contact with the 0 Kelvin environment, because as soon as you put something hot in contact with 0 Kelvin, it's not going to be at 0 Kelvin anymore. It's going to heat up. So the practical limits to what our cycles can do. Some people say that this also outlaws perpetual motion machines, because you can say, well, the heat we sucked out of it, we could put back in the hot reservoir and regenerate it and run this thing forever. And so this is the law that basically makes perpetual motion impossible. So this is what's driving these spontaneous reactions, is order to disorder. So we're familiar with balls bouncing. Okay, so you've got these little rubber balls. That's fun. Yes. So it bounces. We're familiar with what it does. It doesn't bounce all the way back up. So notice how it releases its usable energy, turns into unusable energy. It goes into the table, or goes into heating the ball up. If I had a really super sensitive sort of radiative, like infrared camera looking at this ball, and I could measure, micro Kelvin changes, I would notice if I do this a whole bunch, that ball is going to warm up. This one will warm up even more. Watch this. It doesn't bounce very good at all. Okay. So it's dissipating its energy into the rubber and not storing it and giving it back to the surface. And so these are just some fun little. Okay, so what's going on? Well, as we bounce it, the total energy of the system, the ball plus the floor, is conserved. But the thing that's driving it is the distribution of energy. So we're going from ordered motion to disordered motion, and we're losing the useful energy. Can you bring that screen down just a little bit? Get the bottom of this. It's the on the right there. Yeah. So we're losing that useful energy because it's becoming randomized. Now, this is where we get into the whole Thanos thing about it's not impossible, it's just improbable. You know, we have all of these motions in the table. The energy we put into that table, it's, I guess, possible that those motions could bounce around on this table, reflect in certain ways, and then come back under that ball and bounce it back up, okay, spontaneously. So I could sit here and look for a million years waiting for that ball to just pop off the table. It's one option out of a gazillion. So it's not probable, okay, but it's not impossible.
Isn't that scientists were trying to do when they're trying to fuse atoms together? Because it would be more disordered with like two hydrogen molecules, and they're trying to.
So they're going against entropy for sure. Yeah, yeah. So the way you can go against entropy is if you create more entropy somewhere else. So the energy released would create more heat elsewhere. And so the surroundings would be more disordered than the fused atoms. So it would work, but you got to do something with that heat. Yeah. So same with water. So we'll see hydrogen and oxygen getting together to form water. We have 3 moles of substances and we're forming 2 molecules. So we're going from 3 to 2. So that's a decrease in entropy, but it gives off an enormous amount of heat. And so we're creating disorder in the surroundings, and so our system can go because it's so exothermic. Our system can go forward spontaneously. So I don't know if y'all know the movie Dumb and Dumber, but this is the difference between impossible and improbable. So this guy, he has a crush on this girl, and he finally gets down to asking her, what are the chances, right? And he doesn't understand probabilities. Okay, so this is, be level with me, he says. Oh, come on. Let me start it over. All right. What are the chances? Not good, she says. He's dealing with the information. You mean not good, like 1 in 100? She'd say more like 1 in a million. Brutal truth. So you're telling me there's a chance? So he doesn't quite get that 1 in a million is still not likely. And people still play the lottery, right? That's 135 million to 1. So that means he could try 135 million times. That's right. Someone's got to win. Yeah. So So the entropy of an isolated system increases in the course of a spontaneous change. And so the simplest isolated system is the universe, and nature as a whole is moving towards disorder. So entropy is increasing, but it's still very low. And I say that's a huge deal because this is one of the data points that says that the universe we're in cannot be infinite in the past. Like the universe has to have a beginning because we're still at a low state of entropy. If the universe was infinite in the past, we would already be out of useful energy. All of the balls would have stopped bouncing. Our planet is losing mass all the time. If we had been here long enough, all the mass would be gone. All the oceans would be dry. All of the air would be gone. The sun would have gotten dense enough to explode and obliterate the planets and so on. And we've seen this happen in the life cycle of solar systems and stars and so on. If that continues to go and go and go for an infinite amount of time, we wouldn't have any planets, wouldn't have any stars left. Even I think the black holes would burn out if given a long enough amount of time, because mass is being sucked into the black hole, but it's being destroyed and turned into neutrinos and these massless particles that stream out of the black holes. So black holes emit, but they don't emit visible light or measurable electromagnetic radiation, or I don't know if it's measurable, but it's these neutrinos that stream out of it. So even that mass is being converted into energy in the heart of a black hole. If that's allowed to go forever, again, entropy, we're losing the usable energy in the universe. Now we don't have to worry about it. It's not going to run out anytime soon, but it is a huge deal that we have such a universe with such low entropy. I don't know. I mean, it's a part of the fundamental particles and so on in physics, but as far as being able to tell you what it is, yeah, I don't know. Yeah. Like what's a charm particle? An up quark, a down quark, the Higgs boson. Yeah. Yeah. It's a fascinating area of science, but my goodness, it gets crazy. They think that gravity is like a dance floor effect when someone famous walks in. And so if you're in a big famous dance floor and I don't know, pick someone famous, pick Taylor Swift, okay? She walks onto the dance floor and everybody runs over there to get an autograph, right? Or a selfie with her. That's the Higgs field, okay? So it's rushing by all particles that have mass and it's a drag effect. And so the masses are drug along by the Higgs field towards other massive particles. And so that's a really weird way to describe gravity, but that's sort of the latest theory about gravity. But I don't know if it's right. Yeah. But it's pretty cool. Yeah. Yeah. Because we still, I mean, I don't really sit well with the arrogant scientists because we don't even know what gravity is. We know how to describe it well, like in terms of its mathematics, gravitational forces, yes. But what is it? No idea. What is energy? I've never given you a real definition. I've said it's a capacity to do work. What is that? Right? I mean, what is that? It's a capacity to do work. I've told you how it's used, but I haven't told you what it is. The ontological question. Ontology is the science of being or the logic of being. We don't know what energy is. Yeah, so, yeah, right, right. So this is fun stuff. Okay. Yeah, that's right. Why is there air? Yeah, that's yeah. And so we can, if this is for reversible isothermal expansion of a gas, we can sort of define entropy. And here we can calculate the change in entropy as a function of this by knowing the final volume and the initial volume and so on. Notice temperature's disappeared because it's the change in heat over the temperature. So we canceled out the temperature. So that's the entropy change. Okay, so then, so at 0 Kelvin, here's the third law of thermodynamics. At 0 Kelvin, all the excited state energy has been sucked out of the system. We can really understand that with Boltzmann's distribution, right? We calculated we were always using KT in the denominator, but if that T is 0, we have e to the minus infinity, and the entropy was the minus log of that, Q, and so on. And so the natural log of 1, that ground state Q, is 0, so the entropy is 0 at 0 Kelvin. Again, if this is a measure of disorder, then S goes to 0 as T goes to 0. And the entropy of a perfect crystalline atomic substance is defined as 0 at temperature equals 0. So this is a practical result. We can make tables now that we have a reference point. And it's just super helpful. You've seen the enthalpy of formation tables and the Gibbs energy of formation tables, and this now gives us an entropy table. We can make an entropy table. Let's talk about phase transitions. And so evaporation and condensation of steam at equilibrium with water at 1 atmosphere and 373 Kelvin. Freezing and melting of water in equilibrium with ice at 1 atmosphere and 273 Kelvin. These are, boiling and freezing. You're very, at least in your everyday experience, familiar with phase transitions. We have a whole section of the course on phase diagrams and phase transitions. And so this delta G of melting at equilibrium is 0. And we know that G is H minus Ts, so delta G is delta H minus T delta S. And so we could solve for that change in the delta S. So that's the enthalpy change in that phase transition divided by the temperature at which that phase transition occurs. And so if we're at constant pressure, then the heat change is that delta H. And we can know then that the endothermic or exothermic, freezing and condensation are exothermic. And students, I should say, students mess this up, and they shouldn't. You overthink it. You get into this thermodynamics course and you're like getting confused and so on, and you make silly mistakes. And it's like, if I say the melting of ice, is the melting of ice endothermic or exothermic? Okay, and you think, well, gee, if I put ice in my hand, it's really cold. So you might think, oh, it's endothermic because my hand is cold. Oh, it is endothermic. Yeah, it's sucking the heat out of your hand and melting. So what's the system? Again, think about the system. The cube of ice is the system. And so my hand is supplying heat to the system, and the system is phase changing, right? It's melting. So that's endothermic. Okay, the opposite then would be exothermic. You're freezing water into ice, you've got to suck the heat out of it. You're gonna suck the heat out and you're gonna freeze it. What about boiling? Well, you put a pot on the stove, and if you don't turn on the heat, it's not gonna boil, right? So it's endothermic. You've got to boil the water by adding heat. And then condensation is exothermic. Don't try this at home. Do not put your hand over a steam kettle, tea kettle, and let the steam hit your hand. That's right. It will condense on your hand, and that's exothermic. It will deliver that heat to your skin, and it will burn you because it's condensing and giving off its heat. Yeah. So this is like ways to hurt yourself today. So let's look at variation of entropy with temperature. This is kind of interesting, some interesting plots. Okay. So we have temperature at 0, we have entropy at 0, so we start to raise the temperature. So here we have a liquid, we start with a solid, it's going along, and then this this phase transition where it melts, we have this jump in entropy. Then we have the increase in the liquid state, and then it boils. We have an increase in entropy going to the vapor, and then it just continues to increase. So we have, essentially, we can integrate all of these. So we'll just jump to this bottom equation. So we can, if we stopped at some point along the trail, let's say we stopped here, we're still in the solid, so we would just come up to our final temperature right here, and if we knew the heat capacity of the solid, then we would be able to calculate the entropy up to that point. If we go past the melting part, we bring in this piece, that's the melting. I never liked that they called it the enthalpy or entropy of fusion, because to me fusion is bringing things together. But this is melting is also fusion in science. It's ridiculous. I hate that. Like a salt fusion, if you have a salt and you can treat it like a solid if you heat it up and melt the salt. That's how Caterpillar and their remanufacturing, where they take engine blocks and painted parts, they dissolve it in molten salt and dissolve the paint off. It sounds very aggressive. Yeah. I know that just from a meeting I just went to. Okay, so now let's look at the heat capacities. This is for oxygen. So this is heat capacity over here, constant pressure. Okay, you have a gas, you have the translations, you have the rotation here. This is oxygen, so it's 5/2 R for the translation and rotation. You only have two halves R for the rotation. And then you add in the vibration, you have 7/2 R. So all three, you get up to 7/2 R for oxygen at high temperatures. Okay. Look at what happens with the liquid. We have essentially another 3 for the liquid. So this is liquid. Look at the heat capacity for liquid. So in almost every case, the liquids have a higher heat capacity than the gases. Here's the entropy change. And this is a new thing. What do you think of that? Yeah, 3 solids. That's weird. So some substances have multiple solid phases. What did y'all do for the optimization lab with the oxygen, 4 oxygen atoms? You could put them together in a rhombus. You could do a linear, you could do a T. Now, I don't know if did anybody get a T shape? And then you could do the tetrahedral, the 3-dimension one. Okay. If you had all of those little O4 molecules in a solid matrix, those would be different solid phases. You could have a rhombic phase repeated in a lattice, and that would be a solid O4 solid. And then you change the temperature, and all of a sudden you get a phase transition, and it snaps to the tetrahedron. And now you've got an infinite lattice of tetrahedral O4s. Totally different solid. And so we can have solid to solid phase transitions, which is a little strange. But this is the first time you've seen that in the course. Okay. They have their own enthalpies, their own entropies, their own heat capacities, and so on. And then we have the standard enthalpies of reaction. So let's look at water, the formation of water. So we could look up the standard entropy, I should say entropy, for each reactant and product. And the pure elements must be included in these because of the definition. The standard state is temperature of 0 and entropy of 0. And so here's our tables. So we can look up these formation values, but let's ignore those for now. We're just talking about the entropy. And do we see any trends? I mean, we've got H2 gas. It's got a pretty low entropy. Let's see, here's O2. It's much higher. Here's nitrogen. It's intermediate between the two. Okay. We've got one here. This is very bizarre. Look at that, a negative entropy. That kind of breaks my brain a little bit, even as a professor here, right? Um, what is that? How can it be? It's not below 0 Kelvin. It seems wrong, doesn't it? To have a negative standard entropy. But look at the situation it's in. It's not a single substance anymore. It's aqueous. And so they set up this definition with zero entropy at 0 Kelvin, and they set up, tables with all of these entropy values. And then experimentally, when they dissolve salts in water, what happens? You got a cation, you've got an anion, and what happens in water, this very polar substance, is now you create order in the surroundings of that ion. So it's not just OH minus, it's OH minus in a field of water. That water was very chaotic without the ion. You put the ion in it, and now it's ordered. Not super ordered, but it's more ordered than it was. And so we've seen a decrease in entropy with aqueous ions to the point where if you were to break it into individual pieces, this entropy of making aqueous hydroxide is actually negative. It's just the way it works out with our definitions of the tables. So that's a little weird, but it's just with our definitions of these standard values, many aqueous solutions will have a negative entropy when you form them of 1 molar solutions at room temperature in 1 atmosphere. So don't be bothered by that. It's just what's in the table. Okay, and so we could do that. We'd look those values up. We have to include the number of moles, and so we take that oxygen value and we multiply by 1/2. We've written this out in terms of 1 mole of the main reactant of hydrogen. Producing 1 mole of water, we only use 1/2 mole of oxygen, so we've got to take this into account here. And so this is our standard entropy change, minus 163 per mole of hydrogen and per mole of water. Notice we will write this out for the reaction as written. But notice there's no per moles in here in the units, because those canceled when we did the calculation. It was 1/2 mole of oxygen, and the entropy unit in the deal was joules per Kelvin per mole. And so all the moles are gone. And so you have to look at the reaction. This is per 1 mole of hydrogen and per 1 mole of water. Okay, this is basic stoichiometry, but it's per 1/2 mole of oxygen. And so if you wanted it for oxygen, you would have to divide by 1/2, which means multiplying it by 2. And so you end up with negative 326.8 per mole of oxygen. Okay. Now this is kind of what you were saying earlier when you said fusion. Fusion decreases the entropy. So it should have a negative entropy change. Two deuterium atoms coming together and making a single atom. We've lost 2 particles. So we have a reduction of entropy. But this is exothermic. It's so exothermic that it creates more entropy in the surroundings, and therefore it's a spontaneous reaction. Same thing here. We have 1.5 moles of atoms or molecules in this reactant side and only 1 mole on the product side. So we've lost on average 1/2 mole of substances. And so this would not be spontaneous if it wasn't exothermic. So the delta G, which is spontaneity, so this piece, if this is negative, then this piece right here is positive. That makes it hard for something to be spontaneous, because delta G, we want it to be negative. But if this is super negative, in other words, it's exothermic, then it can overwhelm the reduction in entropy. And so we can have an exothermic reaction be spontaneous even if the entropy is reduced. But if the entropy is increased and it's exothermic, there's no way to stop it. So if you have like a fuel like hexane plus oxygen, you got 1 mole of hexane. Think of how many moles of CO2 it produces. 6 moles of CO2. You've got all those waters. you've got all those, waters, you've got molecules of oxygen that are being broken apart. It's producing a whole lot of moles of gas. So entropy is increasing and it's releasing heat. So that's why it's so hard to stop combustion. Once a fire starts, then entropy is going crazy and it's releasing heat, which increases the entropy all the more. And so combustion is a great thing in control. When it gets out of control, obviously it's so destructive because it's so hard to stop. That's enough for now. That's the second law. So, yay for us.